12.2 is what we did yesterday, essentially. I don't make the content; I just deliver it. So I wouldn't have. I would have. I don't know. I don't think we needed to actually have it as two separate lessons, but it is. And like I mentioned when we started yesterday, that the rules of exponents are the number one rules that pre-cal and even calculus students are still weak in, and we spend a lot of time going over it. So here are some of the rules. You can tell me which one's missing. Um, First rule: when you're multiplying and the bases are the same, here the base is a. We call a the base, and the exponents are m and n. When you're multiplying and the bases are the same, you add them, right? Now, also keep in mind that these things not only work from left to right, they also work from right to left. There are times where we have a to the m plus n, and we want to split it back up into two separate factors. So it does work the other way. Similarly, when you're dividing and the bases are the same, you subtract the exponents. And again, we usually go from left to right, but this also works from right to left. The negative exponent is the one that's in the denominator. Got it? The negative exponent is the one in the denominator. All right, this is exponentiation. When you raise a power to a power, it turns into multiplication. And of course, this works left to right, and it also works right to left. This one is a continuation of the previous one, but it just shows you that if you have multiple factors, right? I'm going to make that word here. These are factors, not terms. Then if you put little ones there, you can distribute, and they each get the factor. And again, it works both ways. If you're dividing a to the first, b to the first, you can distribute the exponent as well. Okay, so it doesn't matter if they're multiplied or divided. You can expand it. You can combine those two into one rule if you use something like this: a squared. Well, let's do this: a to the m, b to the n, all over c to the p power, and then all of that to the um, r power. Okay, this is combining these two rules right here. You can combine it into one rule. So I have two factors in the top, one factor in the bottom. They're all being multiplied or divided, so I can multiply the r through to each one. So this becomes oops. This becomes a to the m times r times b to the n times r all over c to the p times r. And again, you can have more factors in the top, you can have more factors in the bottom. The point is, every factor gets the exponent on the outside, and you multiply. Okay, raising a power to power, you multiply. Now, the new one that y'all learned yesterday is this last one, negative exponent, which is a surprise to me. A to the negative m is 1 over a to the positive m. And this one is important to realize that it works both ways. Because a lot of the times in calculus, we start on the right-hand side, and we want it in the left-hand side format so we can work with it. So negative exponents are fractions in disguise. Negative exponents are fractions in disguise. If you simply want to take a factor from high to low or low to high, all you got to do, if you put that over 1, all you got to do is change the sign of the exponent. Bring a factor from low to high, bring a factor from high to low. All you got to do is change the sign of the exponent. If it's positive, it becomes negative. If it's negative, it becomes positive. Okay, so what rule is missing that you would add? Oh, yeah, I wasn't thinking about that one. Yeah, let's do that. A to the 0 is 1 as long as a is not what? As long as a is not 0. Yeah, as long as a is not 0. Um, I was thinking more along lines of another similar new rule that we kind of recently learned. It rhymes with patical. Radical. The radical rule. I'm good at clues and you're good at getting clues. Yeah. The radical rule. This is relatively new, like the negative exponent rule. If you have the mth root of x to the nth power, that is the same as x to the what power? Nm? N over m. Yeah, n over m. And this one, again, very important that you develop the fluidity, I like that word, of being able to go back and forth from left to right or right to left or left to right or right to left. Or right to left or left to right. Yeah. Okay, so let's jump down to example 1. Simplify the expression. Assume that all variables are positive. Exponents, this is important, exponents in simplified form must be positive. So in our final answer, we don't want any negative exponents. But Is it okay to have negative exponents in the interior of the problem while we're working it? Yeah, very often we like negative exponents because it allows us to take things out of the denominator, and working in the numerator just feels safer. Okay, so let's do this. We'll do this rather quickly. 8 to the 1/3 divided by 8 to the 2/3. What do we do here when we're dividing and the base is the same? We subtract the exponents. Now, you could say it's 8, and then you could write it as 1/3 minus 2/3. You could do it like that, or you might be able just to add those in your head. What is 1/3 minus 2/3? Is it positive or negative? It's negative, and then 1 minus 2 is 1. So if you want to go straight from here to here, that's okay bueno, right? That's okay bueno. Just make sure you add correctly. Now, it said no negative exponents in our final answer. So how am I going to get rid of the negative exponent? Well, here's the easiest way to do it. If it's not a fraction, put it over 1. And then you just bring that to the bottom, and that leaves a 1 on the top. And then what becomes of the exponent at the bottom when you just bring it downstairs? The only thing that changes is instead of negative, it becomes positive. So it's 8 to the positive 1/2. Why did I put 1/2? Yeah. No, it's 1/3. Sorry. Yeah. I'm just checking. Just checking. Part of what my doctor's appointment tomorrow is checking out my brain. I'll bring that up. Yeah, with the doctor. See what he says. Ooh, you should quit teaching math. You think 1/2 is 1/3. Yeah. No. No. This is this rule up here. When you're dividing and the bases are the same, you subtract the exponents. Did the A's divide out here? No. No, if they're different, then you can't really do anything with them. They would stay the same. Yeah, here's why. Look at this. 2 to the 4th divided by 2 to the 2nd. According to the rule, that's 2 to the 4 minus 2nd power, yes? Which would be 2 squared, which is known as 4. When in doubt, you can expand it out. So here's what we're really doing. We're doing 2 to the 4th, which is 2 times 2 times 2 times 2, all over 2 times 2. So when we subtract, we are dividing things out, but we're not dividing out the bases. What divides out here? Those 2's divide out because they're both to the first power. These divide out because they're to the first power. And we're left with what? We're left with 2 squared, which is 4. Now that you can see that in action because we have whole numbers as an exponent. But the rule of subtraction works with any exponent, not just whole numbers. Okay? So no, the 8's don't divide out. Yeah. What's that? Is the answer this whole thing like 1 over? No, this could be one of your answers. Yeah, this is final version number 1. Remember we did yesterday final version? Yeah. Now here's another way to do it. You could now get rid of the fractional exponent if you want. 8 to the 1/3 is the same as what? Cube root of 8. Yeah. And then I'm running out of room left to right, so I'll just go or down. I'll just go left to right one time. What is the cube root of 8? 2. So guess what that entire expression is equal to? It's equal to 1 over 2. Yeah, it's equal to 1/2. Inch by inch, it's a cinch, right? But you got to know the rules. As soon as you violate a rule or you make a careless mistake, you've derailed. Your train is off the track. Okay. So good questions. This would be final version number 2, which would be the simplified version. Any other comments or questions or observations about this problem? You all had good questions. Think about it. If the 8's were to divide out, what would you say you're left with? Would you say with your 1 to the negative 1/3? Is that what you would do if you allowed the 8's to divide out? Okay, well then what is 1 to any power? 1 times 1 times 1 to any power is just what? 1. So by that logic, if this were 9 to the 2/5 over 9 to the 7/8, which are very different, your logic would be, oh, those divide out to get 1 to the whatever power, which is 1. The answer would always be 1, right? And that's not how it works. That's not how it works. So don't divide out the bases, subtract the exponents. Okay. Now you said what if they were different? What if we had like 2 to the 8 all over 8 to the 2nd? We can't do anything as that sits, right? Because the bases are different. The bases are different. But we could do this. We could say that, hey, 8 squared, we can write 8 as the power of 2, can't we? It's 2 cubed, isn't it? Yeah, and now I can combine those. That's going to give us 2 to the 8th over 2 to the what? When you raise the power to power, you what? Multiply. So now I've made the bases the same because I knew 8 was the power of 2. So now I get what? 2 to the what power? 8 minus 6, which is 2, and that equals 4. Yeah. So there is hope when the bases aren't the same, but not always. If that were 2 to the 8th over 9 squared, we really couldn't do anything. Okay, because you can't write 9 as a power of 2. All right, letter B. We have two factors, 27 to the first and x to the 3/4. So notice what I did there. I added the 1 on the 27. It's all to the 2/3 power. So what do we do with the 2/3 to each of the exponents? Distribute. So we get 27 to the 1 times 2/3 is 2/3, and x to the. Now, if you want to do this off to the side, here's your workbench. I'm going to do 3/4 times 2/3. I'm going to do that off to the side. 3/4 times 2/3. Well, what happens with the 3's? They don't cancel, they divide out. And we're left with 2 over 4. What's 2 over 4? 1/2. So this, I'll bring that back into the work now. That's 1/2. Okay? And then the last thing we could do is this. Whenever you have a number raised to a power, you try to evaluate it. Okay? 27 squared, cube root of that, or cube root of 27 then squared. What should we do? Cube root first or square it? Cube root it. What's the cube root of 27? 3. 3 times 3 is 9. 9 times 3 is 27. These will become more commonplace for you. The cube root of 27 is 3, and what's 3 squared? 9. So that was your final answer, 9. Now you can leave it as 9x to the 1/2. This could be final version number 1, but that's the same as 9 times what? X to the 1/2 is the same as 9 times the square root of x. Yeah, this would be final version number 2. And again, notice how I'm doing this. Everything disappeared. I'm working straight down. And we've talked about this all year long. Every line is equivalent to the one above and below. And if I need to do scratch work, I don't do it in the flow of the problem. I do it off to the side so that it doesn't interrupt the flow of the problem. And then I can bring my answer back in. Okay? Get in that habit. All right, comments or questions on B? B is in bursting with bataquatulence. Okay? If you're really, really happy, like I am after that playoff win last night, yeah. Did you see Buford has an account? Buford has an Instagram account, and he posted last night some pictures. And one of the pictures he posted is you hitting Buford's butt as you ran by at the beginning. His account name is Buford the Unicorn. But I also took a bunch of pictures and I shared the link with you and Mr. Lincoln, so it's on there. But Buford has an account. Bursting with bad quatulence. That means that you're excited. Excited. Yeah. Did you find Buford's account? Buford the Unicorn? Yeah. Buford the Unicorn. Yeah. He doesn't post often because it's hard for him to text with his hooves. It takes a lot of time. But when he posts, he's happy. Yeah. All right. Let's go to letter C. Letter C. All right. So taking inventory, I have one factor in the top and two factors in the bottom. The rule up here that I just said, this one that combined both of them, says, hey, just distribute the exponent to all of them inside the parentheses. So I'm going to distribute the 3/2. I'm going to put a 1 on the 16, so I have a target. I'm going to distribute the 3/2, and I'm going to distribute the 3/2. Now, whenever I multiply fractions, I like to multiply them off to the side. So I'm going to get y to the, and then off to the side of my workbench, I'm going to do 4/3 times 3/2. That's the top. Now the 3's will divide out, and we're left with 4 divided by 2, which is what? 2. So now I'm going to bring the 2 back in over there. Okay, cool. Now it's divided by 16 to the 3/2. I'm just going to write it as 16 to the 3/2 temporarily. And then I got y to the, and then I'm going to do it again off to the side. 2/3 times 3/2. What happens to the 3's? Oh, they divide out. Yeah. They cancel like in algebra 1, but they really divide out. And what happens to the 2's? They also divide out. What happens if everything divides out? What are we left with? 1. And that's the difference between dividing out and canceling. Things cancel to give you 0. Things divide out to give you 1. So we're left with y to the first. And then we take inventory and we're like, okay, we got rid of the parentheses. Now we need to combine. I have like bases there, don't I? So what does the rule say when you're dividing and the bases are the same? What do you do with the exponents? Subtract. So what's 2 minus 1? I get y to the 1th. I'll just leave it as y. Now 16 to the 3 halves. We can either do 16 cubed and then take the square root of that huge number. No, thank you. Or we could take the square root of 16 and then cube that number. Yes, please. What's the square root of 16? 4. What's 4 cubed? You'll know it. If you don't know it now, you'll know it later. 4 cubed is 64. 64. 4 times 4 is 16, and 16 times 4 is 64. So 4 cubed is like 2 to the 5th. It's one of those things you'll know. So we get 64. So your answer is y over 64. Y over 64. Now, that's just one way to do it. Remember I said kind of yesterday that there's lots of different ways that can lead you to the final answer. Someone else, instead of distributing the 3 halves right away, might have said, hey, could I have combined the y's inside first instead of distributing the 3 halves? Would that be legal? Yeah, because exponents have the same priority level. Let's see what that would look like. If I were to combine the y's first, I'd have y to the, and then on my workbench, I would say 4/3 minus 2/3. What's 4/3 minus 2/3? 2/3. So I'd get y to the 2/3. Okay, and it would be all over 16 still. And then I would distribute the 3 halves. And what's 2/3 times 3 halves? 1. So we get the same answer. Which way is correct? Both. Both. You just have to map your own way. Okay, but again, notice we're working straight down and everything's equivalent. All right, questions on that? Just more examples, more practice.
When you do the y squared minus the just normal y, how come it just stays on the top?
Oh, because the rule says when you have x to the a over x to the b, it's equal to x to the a minus b. And it's always in the numerator. Your result is, when you use the subtraction rule, your result is always in the numerator. So if I do that right here, that's y to the 2 minus 1, which is y to the first, and it's over 1. Okay? Now again, when in doubt, expand it out. You can actually do that here. That's really y squared, which is y times y over y to the first. The y's divide out, and we're left with a y on the top. But that's a good question. People kind of wonder, when you do the subtraction rule, where do you put your answer? Do you put your answer in the top or the bottom? And the answer is, when you do the subtraction rule, you always put your answer in the top. Yeah, always in the top. Any other comments, questions, or observations? They're good, clean jokes. I got a good, clean joke. Madison girls soccer is advancing to the next round of the playoffs. No, they're not. All right. Okay. Example 2, simplifying radical expression using the properties of exponents. Again, let's read the instructions. Simplify by writing it using rational exponents. So what I told y'all yesterday is whenever you see a radical and you're trying to simplify, get rid of it. Write it as a fractional exponent. Assume all variables are positive, and then here's the last thing again. Exponents in simplified form should all be positive. So no negative exponents in your final answer. All right. Step 1, I spy a couple of radicals, don't you? All right. So what I'm going to do first is I'm going to rewrite the radicals as fractional exponents. And when I do that, I'm going to try and clarify what I'm doing. So I have 3 factor groups. I have the x out front. I don't really need the dot, but we talked about yesterday how it's okay to have a dot to kind of show the separation. So there's that one, and then here's the last one, 4x squared y squared to the 1/3. So the dots are just there, really, to show the 3 original factor groups that we have. You don't really need the dots there. So whether you want to have them or not is up to you. All right, now that I've got them written as fractional exponents, I'm going to come through, and everything that doesn't have an exponent on it, since I have exponents on the outside and I'm about to distribute, I'm going to put little 1s there. Believe me, it helps. It helps. It helps a lot. Now I distribute the 1/3 to all 5 of the exponents. So I got x to the, and I'm going to put a dot, 2 to the 1/3 times y to the 1/3. I'm just going to put a dot in between all of them. Why the heck not? 4 to the 1/3 times x to the 2/3 times y to the 2/3. Yay. Looks like a family portrait now, right? We're all together. There's no parentheses. What does that mean now? Now we need to go through and collect like factors. We have numbers, we have x's, and we have y's. So in your final answer, you should have one number, one x, and one y. Let's focus on the numbers first. I'm going to do this off to the side on the workbench. I have 2 to the 1/3 times 4 to the 1/3. Do y'all remember from yesterday what property of multiplication allows us to associate these two factors together even though they're not written side by side? The associative. Yeah, very good. The associative. Now, can I just add the exponents there? 2 to the 1/3 times 4 to the 1/3. Can I just add the exponents? Okay, let's say you do add the exponents together. 1/3 plus 1/3 is 2/3. What are you going to put as your base? A 2 or a 4? You multiply them and get 8? So you call it 8 to the 2/3? Is that right? No, no, you can't do that. That doesn't work. You can only combine those if the bases are the same. Okay, now you can also look at this route. They're both to the 1/3 power, so they're both cube roots, aren't they? They're both cube roots. Is 2 a perfect cube? No, it's 4 a perfect cube. It is? What's the cube root of 4? It's a perfect square root. It's not a perfect cube root. So here's what we can do. Remember I said right here that this rule not only works going from right to left, but it works from left to right. So if you have two things that have the same exponent and they're multiplied together, you can put them together. Like I said yesterday, you can put them under the same gel cell. So if you want to write this back as a radical, that might be a good first step. Whenever you have numbers and you're evaluating it, we think better in terms of radicals still. So if you want to convert them back to radicals, you can. So now I said yesterday, they're both in cube root cells. We can put them in the cube root cell together. So that would be the cube root of 2 times 4, which is the cube root of 8. So individually, they weren't perfect cubes. But now that I've combined them together, what's the cube root of 8? 2. 2. So this is kind of a divide and conquer thing. We need to have the patience to go off to the side and work on the individual parts, and then we bring the parts back into the problem. So the numbers are done. I got a 2. There's the numbers. All right, let's focus on the x's now. I have x to the first times x to the 2/3. Are those bases the same? X and x, are those bases the same? Yeah, so what do I do with their exponents? I add. Now, you might know what 1 plus 2/3 is in your head. I hope you do. But off to the side, 1 plus 2/3, 1 is the same as 3/3. So anytime you want to create the number 1 and put it in terms of some other fraction, it's just denominator over denominator. 3 divided by 3 is 1. So what's 3/3 plus 2/3? 5/3. There's your new exponent on your x. And then we got y. We got a y right here and a y right there. They're both y's. So what do I do with the exponents? I add them. I add them. Now, this is going to be a little bit easier because they're both fractions, right? 1/3 and 2/3. What's 1/3 plus 2/3? 3/3, also known as 1. So I don't even need to write the 1, do I? So this could be final answer version number 1. It could be. But there's no negative exponent, so that's good. But I could write the middle one as what? There's two different ways I can write it. Is that the 5th root of x cubed or the cube root of x to the 5th? Cube root of x to the 5th. Yeah, times y. This could be final answer version number 2. I like both of these. Either one of these work for me. Now, here's what Algebra 2 might have you do. Your worksheet, your homework might have you do this. We did this yesterday. You can actually simplify this radical, okay? Because remember, the cube root of x, we'll do this off to the side on the workbench again. The cube root of x to the 5th is really the cube root of x times x times x times x times x. Yes, yes. How many factors of one type on the inside does it take to make one on the outside? It's a cube root. It's 3, right? It's a cube root. So it takes 3 on the inside. So I can pull one of those x's out and leave the other 2 left on the inside. So you could also write this as 2x cube root of x squared and then y off to the side. But this to me is yucky, yucky, gross, gross. I don't like it. YYGG. Yucky, yucky, gross, gross. We typically don't do that in advanced levels of mathematics. We like to keep the x's together. We like to chunk them together. I'd rather have an x to a power or a single x under a radical. I really don't want to split them up into x to the something times x to the something. But after previewing your quizzes or your homework, you might have to do that. Okay? You could do a factor tree as well. If you wanted to do a factor tree, you could have done x to the 5th factor tree. That's x times x to the 4th, and then it's x times x cubed, and then it's x times x squared, and that's x times x. And because I look for pairs, or I look for threes, right? Groups of 3, there's a group of 3, 1 comes out and 2 stay on the inside. You could do that. But anyway, I don't like that version. But it could be. It could be a final answer. All right, comments, questions, quips, quotes, concerns. Girls soccer plays tomorrow in Buda at Johnson. If you're interested in going, 7 o'clock, I think. Yeah, Lake Travis. Yeah, they're all right. Not as good as we are. Yeah, they're more into skiing over water skiing than soccer, seeing as that they live on the lake. So letter B, the square root of 64y over the cube root of 64y. Ooh, 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 you're saying the 64's divide out, the y's divide out, even the radical symbols divide out, and we're left with 3. Give me my 100. Does that work? Not even. Not even. It's not even a funny joke. Okay? A good math teacher might have a heart attack if he sees you doing that. That's not funny. Now here's what I would do. There's 2 factors under each radical. If we're trying to simplify a number, we want to leave it in radical form. If we're trying to simplify a variable, we want it in exponent form. Okay? Because everyone knows better that the square root of 64 is 8, better than 64 to the 1/2 is 8. So here's what I'm going to do. I'm going to split it up. The square root of 64 times y to the 1/2 power, all over the cube root of 64 times y to the 1/3 power. So I left the numbers in radical format, and then I put the radicals on the variables in exponential format. Are you okay with that? Okay. Now we go to the next line. We try to evaluate. What is the square root of 64? We already know that. It's what? It's 8, right? Bless you. Bless you. You're quite welcome. And what is the cube root of 64? 4. Y'all are all over that now. Okay? And then I just have these y's to divide out, but the bases are the same. So what do I do when I'm dividing and the bases are the same? I subtract. So off to the side of my handy dandy workbench, I'm going to do 1/2 minus 1/3. You know how to do this quickly in your head? Crisscross applesauce, butterfly, multiply. Start in the top left, like you're reading a book. You start in the top left. You multiply across, and you get 1 times 3, which is 3. Then you take the middle sign, and then you do the bottom left times the top right, crisscross. 2 times 1 is 2, and then it's all over the product. 2 times 3 is 6. So 3 minus 2 is 1. You get 1/6. That's the shortcut way to do it. The other way to do it, 1/2 minus 1/3, is just to say that the GCD is 6. So you multiply this one by 2 over 2, and you multiply this one by 3 over 3, and you get 3, 6 minus 2, 6, and you get 1/6. It doesn't really matter how you do it, but that little crisscross applesauce is a quick way to do it. Top left, start like you're reading a book, top left times bottom right, middle sign, and then bottom left times top right, all over the product of the two. So we get 1/6. Now, That means it's going to be y to the 1/6. Caden, do I write y to the 1/6 in the bottom, or do I write y to the 1/6 in the top? In the top. So you've already anticipated that. I was going to ask that question here, but you already asked it earlier, so now everyone knows when you do the rule, you write it in the top. Okay, are we done? Is this simplified enough, or can we go further? I think we can go further. Look at your numbers. Whoa, I erased it instead of highlighted. Stupid eraser. 8 divided by 4 is what? 2. So I get 2y to the 1/6 power. This could be your final version, number 1. The other version could be putting it back as a radical, which y to the 1/6 is the same as what? The 6th root, yeah, the 6th root of y to the 1st, which is y, the 6th root of y. Does the 2 go onto the radical with the y? No, because the 2's exponent is a 1, not a 1/6. Okay, so this would be your final version, number 2. It's fun. It's easy. It's getting to be fun easy. It's getting there. Right now, it's just still fun, moderately challenging. Right? Yes, yes. All right. And then simplifying radicals. Simplifying radicals. This is where we make the factor tree, okay? Rationalize any irrational denominators. What does that mean? Rationalize any irrational denominators. That basically means no radicals in the denominator. Ooh, no radicals in the denominator on our final answer. Okay, if you say so. Step 1, I have the cube root of a single term. There's 3 factors in there, 3 factor groups. I have the number, the x, and the y. I'm going to take the cube root of each of them, okay? But again, what I'm going to do with the number is I'm going to leave the cube root intact, and what I'm going to do with the variables is write it as an exponent, okay? We think better with radicals on numbers. So this becomes the cube root of 256 times x cubed to the 1/3 power times y to the 7th to the 1/3 power. Each of the 3 factors get the radical. The number keeps the cube root. The other 2 get raised to the 1/3 power. All right, now let's focus on the cube root of 256. Is 256 a perfect cube? I don't know. I don't know. But we do know that we can factor it to its prime factorization and pull out triples, don't we? So let's do that. 256. Anera, give us 2 numbers that multiply to give us 256. How about this? Do we know it's even? Is it an even number? Yeah, so I know it's 2 times something. 128? 128. 128 is also an even number, right? So I know it's going to be 2 times 64. Let's just keep it going. 64 is even, so it's 2 times 32. And 32 is 2 times 16. And 16 is 2 times 8. And 8 is 2 times 4. And 4 is 2 times 2. I lost track of how many 2's that was. Okay? So here's the prime factorization. 2. I can circle triples of them. So let's circle triples. Here's a triple. So one of those comes on the outside. Here's a triple. One of those comes on the outside. And I have 2 left. So those stay on the inside. So now it's the cube root of 2 squared. All right, that's my first step on the numbers. My first step on the numbers. Now I'm going to look at the x. What do I do when I raise a power to a power? What do I do with the exponents? Multiply. What's 3 times the third? It's 1. So I get x to the first. Very good. X to the first. And then I got y to the 7th to the 1/3. That's y to the 7/3. So that's just my first line. Don't expect to get the correct answer in the first line. The first line is just the first step. Okay? Now let's see what we could do in the number category. I know 2 times 2 is 4, and that gives me the cube root of 2 squared, which is also 4. So there it is. The cube root of 256 apparently is 4 cube root of 4. Times x. I don't need a dot. You can put a dot if you want. Times x. And then times, we'll just leave it as y to the 7/3. This could be your final version, number 1. Okay, this could be your final version, number 1. But of course, we kind of have mixed notation there. We have a cube root and something to the 7/3. So here's the other version. 4 cube root of 4 times x times the cube root of y to the 7th. That could be your final version, number 2. So you should be real fluid at going back and forth from rational notation, rational exponent notation, or fractional exponent notation, to radical notation. We haven't seen a lot of negatives in here, but remember, a negative is a fraction in disguise, and a fractional exponent is a radical in disguise. And that's it. We're done. Neither one of them are very pretty, but hey, what are you going to do?
You put the 4 and the y, the 7 the same.
You can. We did that yesterday. I was wondering if anyone was going to bring that up. These are both in the same cube root prism. Now, I chose not to do it because we have number, x, and y, and we like to write our answer in number, then in alphabetical order, x, y, z. But yeah, there's no reason why we can't do it. The associated property tells us we can. So this could be 4 cube root of 4y to the 7th under the same prism cell times x. That's final version number 3. Very good. Very good. And again, notice we're working straight down. Everything is equivalent to the line above and below. There's no equal signs even, are there? We don't even need equal signs. If you're working straight down, you don't need equal signs. Good stuff. All right, the 5th root of 32 over x cubed. I have the 5th root of a quotient. I'm going to give them both the 5th root. The top is the number, so I'm going to keep it as, I put the cube root. I'm going to keep the top as the 5th root of the number, and the bottom I'm going to write it as x cubed to the 1/5 power. They both mean the same thing, right? The 5th root to the 1/5 power, they mean the exact same thing. So the variable I'm putting as a fractional exponent, and the number I'm leaving as a radical. If I ask you what 32 to the 1/5 power is, you might try to do 32 divided by 5. But if I say what's the 5th root of 32, you're like, ooh, I know that now. It's what? It's 2. Yeah, it's 2. All over x to the 3/5. Now, this is where it gets kind of tricky. It says no radicals in the denominator. Do we have a radical in the denominator? We do. It's in disguise, though, isn't it? Just like when I do this, you're like, where did Mr. Korpi go, right? Where did Mr. Korpi go? And I'm like, it's me. It's just a fake mustache, right? It's me. I'm just in disguise. This is the same as 2 over the 5th root of x cubed. 5th root over x cubed. So I do have a radical in the bottom. There are 2 ways to clean this up. I'm going to retreat back to the top line. The first way to get rid of the radical in the bottom is simply to bring it to the top. That gives us 2 times x to the what power? If I bring a factor from high to low, negative. So I can say to the negative 3/5. That's one way to take care of the radical in the bottom. I've written it in the numerator, but to a negative exponent. So that can be final version number 1. But here's the better way to do it, because really if you have a negative exponent in the top, you still kind of in disguise have a denominator, which means you still have a radical in the denominator. It's just in a really good disguise. It's in a fractional exponent and a negative. It's 2 disguises in 1. Here's what we really should do. What we try to do to get rid of the radical is we try to make the exponent in the bottom a 1. Okay? We want the exponent in the denominator to equal a 1. That would make the fraction go away. If we can make the fraction go away, we don't have a radical anymore, because the radical is the fractional exponent. So I'm going to multiply by a clever form of 1. X to the something over x to the something. So here's how we decide what the exponent needs to be. I have a 3/5 right now on the exponent. What do I need to add to 3/5 to make it whole? 2/5. Yeah, 2/5. I have 3 parts out of 5. I only need 2 more parts out of 5 to make it whole. So if I multiply by x to the 2/5 over x to the 2/5, here's what happens. In the top, I get 2x to the 2/5. And in the bottom, I get what? X to the, what's 3/5 plus 2/5? 5/5, which is equal to 1. So I get this right here. So this could be your final version number 2. Now, remember what I just said earlier. We don't really see that version a lot in pre-cal or calculus because now we've split up our x's. In fact, if you saw that, you might want to do the rule that says, hey, when the bases are the same and you're dividing, subtract, right? You might be tempted to do that, okay? And I wouldn't blame you for that. We like our x's to be unified. We want this version really, or this version here, final version number 2. This also works. I like this. But this could be final version number, not 2, this could be final version number 3. I just don't like that version. This one's kind of yucky, gross to me. But that's how you get rid of the radical. You rationalize the denominator by getting rid of the rational exponent. Yeah. And that concludes today's notes, right? Kind of the same thing we've been doing, but just more practice with it. Any comments or questions? When is this homework due? Yeah, 12.2 homework is due Wednesday. 1 week from today. There you go. Yeah. Um, and then 12.1 and the review that we did, page 2. Page 2. That's due when? Yeah, tomorrow. That's due tomorrow at, I think I said at 4:20. Yeah, and this is due at 9 a.m. Okay, and you have all day tomorrow to work on any one or all of those three. Sound good? Sounds good to me. Okay.